Okay, so we will begin. Hello, guys. Right now, we are here to present the topic, the game theory approach to urban public transport integration policy. So the presenter is me, Xiao, and Jiayi. So we were introducing the following order. First, we will introduce the background, and we will offer the game theory framework. Of course, we will also provide the case study of the game theory framework, and we will give the conclusion. First, the background is that we are here to research on the urban policy, transportation policy. So the improved integration benefits customers, but does not guarantee improved payoffs to the individual transport operator in the market. The previous research provides guidelines for policymakers but attributes little insight to the individual transport operators. Insight of underlying strategies of operators are crucial to the integration implemented by the authorities. This is why we have to research on the urban transportation integration policy. But why game theory? Why we try to apply the game theory in this problem? Since we all know that the game theory is the study of conflict and cooperation among individual decision makers, and the game theory can help us to provide understanding of market dynamics and predict equilibrium. Of course, it can also assist both operators and authorities to formulate and optimize their strategies. So in the urban transport market, we have two main players. The first one is the transport operators, they provide the bus service or train service or other transportation services. And another one is the authorities. They decide to regulate or deregulate the market. So in order to get the whole framework of this integration problem, first we have to define the transportation integration on the operator's level, since we care about how functional integration will affect social welfare from the authority's view. And of course, we have to be clear about the effective forms of transportation market. Like right now, we have only two market structure. So the first one is the operators competing in the same district. And the second one is the operators running services in the separate district. And this is in line with our common sense. The game formulation is provided as the picture. Assume we have many operators, and each operator I will has a finite set of strategies, concerning integration Si. And each operator I chooses a strategy and receive a payoff of mu I. And here we give the payoff function of each operators given n strategies. As we can see here, the expected payoff is the fair price of a certain transportation service and multiplied by the ridership. And then you have to subtract the cost of this ridership, and then you have to also subtract the integration investment. As you can see here, the cost of ridership is represented as a linear form, since CI here is a baseline generalized operation cost for operator I, and the KI here is a cost factor based on ridership. The integration of the strategy is the investment, like RISI here, is the investment contributed by operator I for an integration strategy SI. It is obvious that all SI strategies do not contribute equally to total system integration, nor do all operators contribute equally to a specific level of integration. Therefore, we will know that the following sigma form will be less or equal than the Imax, where Imax is investment required for total integration. So the Nash equilibrium here can be defined as a set of strategies in the following equation. So this is actually a social optimal solution. And to find the Nash equilibrium, we need to set the derivation of expected payoff to in terms of the integration strategy to be zero. So in general, like we provide five strategies here. And the first strategy, S0, is no integration. And of course, the respective investment would be zero. And the second is the fare integration. So the provision of a uniform fare enabling passengers to travel from one operator to the other without extra fare. Well, in this case, like the respective investment is very close to zero. And for the third one, the common stations and rerouting of buses. For example, like this can be enabling passengers to seamless transfer from one operator to the other, well, with the respective investment not be zero. And we can also offer the scheduling strategy, which is able to enable passengers to transfer from one operator to the other with minimum time loss with the respective investment. This is also not zero. And finally, another strategy that is available is provision of information. Here, this strategy will help passengers to organize and program their travel from one operator to the other, so with also a non-zero investment. Well, to think about the integration effect, we have to first consider about like the sum of ridership after integration. So here we have three cases. The first case is the synergy case, which means that the sum of ridership will increase after integration. So this is shown in mathematical formula, like the first, like the derivation of the whole ridership in terms of the strategy will be greater than zero. And also the additivity means that the sum of ridership is indifferent after integration. So mathematically, the derivation, the first order derivation should be the zero. And also the substitutability, which means that the sum of ridership will be fewer after integration. Well, so it should be less than zero. So right now, my partner will introduce the following part.
All right, let me continue the presentation for some concrete cases. Let's now consider two major categories of operators and market structure. The operators competing in the same district and the operators running service in the separate districts. The problem is initially addressed by focusing on a two-operator market, for example, a two-player game, and then extended to a compensate for a multi-operator one, for example, a multiplayer game. Now let's focus on two-operator integration. The two-player game is a simplified one and describes the cases where two transport operators provide service in the same market. And the Nash equilibrium of a two-operator market is shown in the picture, where we differentiating the expected pair of mu I to Si and set them to zero, and we can get the result, which indicates that a first optimization may be achieved by introducing a unified fare, as well as the synergic result of integration. And we can find some evidence in several cities with deregulation. Under the condition of unified fare, we can introducing F1 equals to F2 equals to F. And under this condition of synergy, in this case, synergy means that the sum of readership increases a number of combinations of fares and service frequencies which achieve a given level of profitability, but not all will be equally effective in terms of public policy objectives. In the case of operation in separate districts for two-operator integration, this system would form a cooperative two-person game, especially a minimal social situation game. And in this case, public operator undertakes the full investment to obtain the full integration. And we can see these modes in the example of Taiwan. A characteristic example is reported by Lang at 2006 in Taiwan, where a decline in bus passengers was initially observed with the introduction of the metro eventually turning to increase after the implementation of integration measures. In the case of operation in the same districts for two operator integration, the operators will act upon the probability of the result assigned to each available strategy, thus leading to various forms of zero-sum or mixed motive games. And in this case, synergy can only be accomplished in the case of market growth. Otherwise, service quality would decrease, which finally reduces the readership. For example, the city of Melbourne, where the introduction of a unified fare increased ridership, but the need to secure payoffs by the private operators lead to a deterioration of service and finally a decrease in passenger usage. Just like the case before, we found that accompanying integration measures will be undertaken by the public. For the case operation in separate districts for multi-operator integration, the situation is very similar to the two-operator case we analyzed before, but there is one additional variable, that is opportunity cost. Under this condition, the individual operator will opt for the one which will maximize expected payoffs, leading dependent operators maximize returns by impairing service quality. And without regulation, market service decline and leading to market leader. In the case of operation in the same district for multi-operator integration, power distribution will formulate the basis for a partially cooperative multi-person game where coalitions may be formed concerning integration. Total integration does not seem as a likely outcome in this case. And investment integration is either contractually induced or measures have to be initiated and implemented by the overall responsible urban public authority. Now we can draw four conclusions for this project. The first is based on market structure and integration measures. Four games and five strategies were identified respectively as we shown before. And the second conclusion is that in all cases analyzed, total integration could not be effected in a purely deregulated system stemming from market mechanisms. And the third one is that unless otherwise induced, the public operator or the dependent operator will undertake the full cost of integration, leading to service deterioration. And the last conclusion is that the development of coalitions is predicted as an unavoidable consequence of a multi-operator market. Okay, that's all. Thanks for watching our video.